We're gonna try another example with application of ideal gas law. Given a stream of air enters 7.5 cm ID pipe. When you see the pipe with the ID, it means inner diameter. Okay. Now stream of air enter a pipe, and the pipe ID1 is 7.5 centimeter. Velocity is, let's use U. Temperature 1 is 27, and pressure is, say, gauge pressure 1.8 bar. Okay, at the point downstream, the airflow 5 centimeter pipe at 60 degree. So in the downstream, the pipe go down to 5 centimeter in the ID. And ID2 is 5. Volume, velocity we don't know. And temperature 2 is 60. And again, this gauge pressure is 1.53 bar. Okay, the temperature is, one is 27, the other 60 degrees, so it's above 100 Kelvin, and the pressure is around 2 to 3 atm, so it's still not very big, it's still low pressure. So we can go ahead and assume air is behaving like ideal gas in this condition. At given condition. Then we can go ahead to apply ideal gas law. Well, because it's given velocity, air flow in and flow out. So we can use flow rate. We can apply volumetric flow rate and molar flow rate to the ideal gas law. Well, you can actually draw a system boundary. In this way you can see this mass flow in and flow out. Next, we're gonna convert every term in this equation to absolute value. Well, given the pressure is gauge pressure, then we have to convert that to absolute pressure. P1 absolute, we know absolute pressure is equal to gauge pressure plus atmospheric pressure, and atmospheric pressure is 1 bar. It's 1.0132 bar, but let's use 1.01 bar. Then we get do the same thing to the downstream. Absolute pressure is 1.53 plus 1.01 bar. Then we got 2.54 bar. Okay, now we have absolute pressure and temperature. We have to convert temperature to Kelvin. This is 300 Now we have pressure, temperature in absolute value. And another thing I'm gonna talk about is the volumetric flow rate in the pipe system is equal to the cross area A times the velocity of the substance flow in and flow out. And because the diameter is given and area is pi times diameter divided by 4 pi r square, and you know r is d divided by 2, so take that square and you get this. Therefore we got a1 is pi d1 square divided by 4, and a2 is pi d2 square divided by 4. And now we can go ahead to apply the ideal gas law to both input and output compared to the state. So we have P1, A1, because V1 we can substitute with A times U, so P1, A1, U1 divided by P2, A2, U2. And because it's the same stream of air going in and out, therefore the mole number is the same. Well, we can write like this: N1, N dot 1 is equal to N dot 2 is equal to N dot, based on the conservation of mass. In this case, we cancel the M because they are the same. Then we had T1 over T2. And because we know A is pi times d squared divided by 4, therefore A1 to A2 is actually, we can cancel all the constant, then we get d1 over d2 square, d1 square over d2 square. Therefore equation can be further converted to P1 d1 square U1 divided by P2 d2 square U2 is equal to T1 over T2. Okay, now we can derive U2 is equal to what I can cross. Then T2 P1 d1 square U1 all over T1 P2 d2 square. Okay, now we can substitute the equation with the number given. We have calculated that T2 is 333 Kelvin times P1 is 2.81 bar times 7.5, well, because centimeters, so we have to convert that to meter square, and U1 is 60 meter per second, all over T1 is 300 Kelvin, and P2 is 2.54 bar. The good thing about this formula is that you don't have to convert all the unit. Just make sure they can cancel out and get the desired unit you want. Okay, this is U2. Now we can cancel the K, bar, and meter. We only have meter per second. Then we get 165.76 meter per second.